Thank you for all of you that showed up today to the second BioXFL lecture in this series. This month we have Joe Luft. He's our resident expert in crystallization here at HWI. And today he'll be presenting some of the theory and practices of nanocrystallography and some of the recent advances in the field. So for those of us that missed this, the presentation and the PDFs will be up on the website after this. And so from here I'll let Joe take it over.
That they can chat in questions.
Right, and if you have questions you can type them in or you can just speak as we go. Thanks.
All right, thanks, Bill.
Yep.
So my name's Joe Luft, as Bill just said. I'm at the Hoffman Woodward Institute, and I'm going to talk today about specifically about soluble proteins, not membrane proteins, and how they relate to protein crystallization phase diagrams and how that relates to the size of the crystals that are formed. So there's not a lot of literature out there that talks about how to grow many small crystals. Most of the literature is going to focus on how to grow single large crystals for standard diffraction analysis. But the same theories and the same phase diagrams can be applied to produce small crystals instead of large crystals. And I'm going to hopefully relate how that can be done during this lecture. I also want to emphasize I'm not going to talk about lipidic cubic phase crystallization, protein work. So this talk is going to cover a lot. It's going to start with the basics of protein preparation and just briefly discuss that, and then get into some of the theory and practical ways to produce many small crystals that could be suitable for XFEL's work. So crystallographers just use crystals to visualize structures, and the structure helps us to understand how the machinery functions. XFELs can actually capture the structure at different time points during a enzymatic process so that it can determine the shape of the structure during that and structural changes that take place during that process. Okay. So when you think of crystallization, all we're talking about is a sample preparation method. It's nothing more than that. It's something that's required to use crystallography to get the structure. Okay. Now, typically, as I said, we're trying to identify initial crystallization conditions. So we're going to take our protein, we don't know how to crystallize it, and we're going to set it up against a wide variety of different chemicals that cover a broad range of chemical space, typically where proteins have been shown to crystallize in the past. And then, once we identify a few conditions where we can get some initial crystal hits, we're typically going to take and use those to produce those conditions and optimize them to produce a small number of large enough crystals to use for standard synchrotron-based diffraction analysis. Okay? But we're doing something very different for XFELs. Okay? Instead of trying to identify conditions that or optimize conditions to produce a few large crystals, we're going to try to produce a large number of very small crystals for the diffraction analysis. So it's a backwards way to look at things for traditional crystallizers. But as I said, all of the theories and all of the mechanics are the same. It's just thinking about things in slightly different fashion. So an important thing to be able to do is to be able to figure out when you actually have small crystals, submicron crystals. And that's not always an incredibly easy thing to do, but there are ways to distinguish microcrystals from amorphous precipitates, randomly ordered proteins that can become deposited in a solid phase in their experiment drops. So typical characteristics of amorphous precipitate, these randomly aggregated proteins, are that they won't go back into solution if you add a small amount of water back to the experiment drop. They will not absorb dye because they don't have solvent channels the way that protein crystals do, which can absorb the dyes to let you know that they are actually crystalline. And typically an amorphous precipitate won't show up when you look at it using traditional or standard UV fluorescence techniques that can detect proteins. Okay. Now, microcrystalline precipitates or nanocrystals, they produce a very different looking precipitate. It tends to be patterned, so it's not a uniform distribution of particles throughout. If you look at it under a microscope and you adjust the light source, you might be able to actually see reflections and get a sand-like appearance to the precipitate. Most microcrystals will show weak birefringence depending on the symmetry and orientation of the crystal. You can get, the crystals will rotate polarized light, which you can use to detect the crystallinity. If you add a small amount of water to an experiment drop that has these pattern precipitates, oftentimes the microcrystals will actually go back into solution very readily. The microcrystals, like larger protein crystals, are made up of protein plus water. They're disordered water that's maintained in solvent channels. And small molecules such as dye can go into those solvent channels and concentrate, so the crystal will have a blue appearance. In this case, this is Isic dye or methylene blue dye that's been added to a ordered precipitate of nanocrystals, and you can see that the dye is taken up by the precipitate. You get a UV fluorescence signal. These are actually too big to be called nanocrystals, but in the image you can see a UV fluorescence signal from these protein crystals. And finally, and what I'm going to talk about next, is a relatively new technology called sonic. It's second order nonlinear imaging of chiral crystals. So this is a very sensitive method that was recently developed, and sonic is a way to detect crystals that are less than a micron in size. And Formulatrix actually sells something they call the sonic, which combines the second harmonic generation signal, which can tell you if something is crystalline, depending on the symmetry. Higher symmetry will not give an SHG signal, and a UV2 photon excited fluorescence signal, which can tell you if something is actually made up of protein. So you can verify the crystallinity with the SHG signal and that the material is protein with this UV2 photon excited fluorescence signal. And this is a very powerful tool for identifying nanocrystals. And just to give you an example now, this is looking at the same drop with visible imaging from the sonic, which if I saw that, an image that looked like that, I would maybe say it was microcrystalline precipitate, more likely just precipitate if I look quickly. But when you see the second harmonic generation, you can definitely see the white signal that tells you that you're actually seeing crystalline material, and the UV signal is telling you that that material is not just crystalline, but it's protein crystals. So you're not getting some random effect of the protein buffer solution reacting with the crystallization cocktail. So this is a way to verify crystallinity and that the sample is actually made out of protein. Now, when we use a technique like the sonic, we actually see that we identify roughly 2.5 times more crystallization leads than we do using just visible images. And the reason for that is, if you look at the bar graph here, is just showing you the number of images that were classified as crystals just using visible images with the blue bars, and the red bars are showing images that contained crystals based on the sonic detection. Again, it's about 2.5 times the number of crystallization hits that were identified. And for each of these 4 samples, we set up 1,536 individual crystallization experiments. So it was a pretty good sampling. And the reason that we're able to see more crystals is we're not just looking for things like the blue square on the bottom that shows visible crystals that pretty much anybody could identify as crystalline. We're able now to detect things like the red box on the top here, which in the past we would have never ever tried to optimize or consider crystalline. By using the sonic, we can see, yes, these actually are, this is crystalline material, or there are crystals behind that aggregated precipitate. So we're actually able to detect nanocrystals where in the past we didn't see anything. Okay. I'm going to skip backwards now, I guess, and talk a little bit about preparing proteins for crystallization. So the protein is by far the most important variable in the crystallization experiment. And the same rules apply whether you're trying to grow large crystals or very small crystals. You want to start off with a pure protein. You want to have some basic knowledge of crystallization, use rational approaches, and pay great attention to details of the experiment. So slight changes in temperature, holding a sample tube in your hand instead of leaving it on ice. Very small factors that some people would ignore can be the differentiator between getting crystals and not getting crystals. So attention to detail, whether you're trying to get large crystals or small crystals, is absolutely critical. Taking good notes, and most important of all, starting off with a pure protein that's consistently prepared during different crystallization trials. If your protein is different from one set of experiments to the next, you're going to get very different outcomes. Things aren't going to be reproducible, and you're going to be very frustrated. So when you're getting your protein ready to go into these initial crystallization trials, you want to be sure first that it's soluble and stable over time. Now, when you're setting up a crystallization experiment, things don't often happen immediately. It could take days or weeks for crystals to form. So if the protein is decomposed before it goes into the trial or during the time course that the trial requires to actually produce crystals, you're never going to get those crystals to form. So things you can do to characterize the protein to make sure it's pure, to make sure that there's it's monodispersed, it has a single size aggregate in the solution. It could be a monomer, it could be a dimer. You want to be sure that the protein has a standard of activity that you maintain, if it's an enzyme, which again can be measured. And you want to prepare it in a minimal buffer. And the reason you want a minimal buffer is just you don't want to dominate the crystallization experiment by the protein buffer. You want the crystallization cocktails that you're using to actually manipulate the chemical environment of the protein solution to promote ordered aggregation or crystallization. So minimal buffer can be a lot of different things, right? You typically want to keep the concentration of the buffer that you use to maintain the pH of the solution relatively low, again, because you want to make sure that the protein is not being sort of held at one pH that's very different from the crystallization cocktail, because if you do that, then you're essentially not screening the variable of pH that you want to screen in your crystallization cocktails. But it's very important to make sure that you have the minimum number of chemicals present that you need to maintain the stability and solubility of your protein. So oftentimes proteins might require ligands or cofactors to maintain their stability, to reduce conformational flexibility, to make them more amenable to crystallization. I'm not going to go through all of these different chemicals that are on this list, but these are just some examples of things that people will add to their proteins to help stabilize them for crystallization. Another very important technology that can be used is differential scanning fluorimetry. And this can be used to identify small molecules that help to stabilize conformationally flexible proteins. Again, I'm not going to go into great detail here, but it's a relatively easy technique to do in the laboratory with a real-time PCR machine. And being able to identify conditions where you get a nice melting curve for the protein can be the difference between getting no crystals or getting crystals like the one that appears on the right side of the screen here. So if you're interested in the technique, there's some great articles out there. This is just one of them referenced on the bottom of the slide. I think the final thing I want to talk about for the protein is, or one of the final things, is just ways to increase the protein solubility using buffers and salts. More soluble proteins, proteins that are put in a solution where they are more soluble, tend to have a higher success rate for crystallization. And being able to achieve those higher levels of protein solubility can actually be beneficial for producing nanocrystals, as I'll show later on in the talk when we start to look at phase diagrams. And again, I'm not going to go into any great detail, but you can gain insight about chemicals that might affect or promote protein solubility from your initial crystallization screen, or by doing specific experiments that are designed to increase the solubility of the protein and then measure the solubility using techniques like UV absorption. So again, if you're interested, there's some articles that you can look up below. General recommendations for storing the protein for crystallization. So we have a crystallization screening facility at the Hutton Woodward Institute, and we receive proteins from many different labs to crystallize. And there are just some general recommendations for people. If you're sending a protein in or you're preparing to do crystallization experiments, you never want to lyophilize your sample. Freeze drying actually rips water molecules away from the protein, and some of these water molecules are required to maintain the protein structure. So if you rip them away, the protein never refolds properly, even after you add water back to the protein solution to rehydrate it. Freezing, you want to do it very quickly. Slow freezing tends to have shear forces and tends to denature the protein worse than a flash, like liquid nitrogen freezing of the sample. You want to thaw the sample very quickly. And basically, it's a very good idea to sort of characterize how the protein stability changes over time when you store it at room temperature 4 degrees, -20, -80, just to make sure that you're storing the protein under conditions that are amenable to taking it back out to use for crystallization trials. Okay, and the other important thing is to aliquot your protein. You don't want to have all the sample in a single tube and freeze it and thaw it many times during the process of doing different experiments. So setting up small aliquots, storing all of the aliquots at whatever temperature you decide to store them at, say -80, and then just taking out aliquots as you need them, and leaving the rest frozen. So, screening, okay, this is taking your protein solution now and combining it with a lot of different chemicals to try to identify some initial crystallization conditions. Okay? It's really not possible to predict how to crystallize a protein by looking at the amino acid sequence or any other physical property that you can measure. So the way that we tend to crystallize proteins to come up with those initial crystallization conditions is just to drive the protein to a state of supersaturation chemically. And we do that by taking the protein and combining it with a wide array, a vast number of different chemical solutions. And these solutions will typically have at least 3 components. You're going to have a buffer that's going to control the pH of the solution. You're going to have some kind of a precipitating agent, which could be a polymer like PEG. It could be a salt, such as ammonium sulfate. That's there to help drive the protein to a state of supersaturation, promote protein-protein intermolecular interactions. And then sometimes you can have chemical additives present that will just help. Some of them that can act like freezers, which will help to stabilize intramolecular interactions to make the protein more rigid for crystallization. Or they can promote intermolecular interactions to actually promote the crystallization process. Now, crystallization screening is really just a sampling problem. If we could take our protein and set it up against every possible variable of temperature and chemical variables that could affect the crystallization or the solubility of the material, there would be way too many experiments to actually effectively ever be able to set up. So we know that proteins crystallize from a diverse range of chemical conditions, from different temperatures, and the temperature affects solubility. But what we have to do is decide upon some acceptable sampling scheme. And I'm not going to go into great detail here, but just to say that we never screen every possible chemical variable because there are just too many of them. So what we have to do is sort of pick and choose screens, conditions of 96 or 24 or 48 or 1536 different chemical cocktails so that we can sample chemical space in a way that makes sense to help identify these initial crystallization conditions. So if after you set up a reasonable number of experiments and you don't get crystals to form, it's best not to just keep purchasing commercial screens and setting up more and more experiments. It's best to rethink the experiment, go back and do something to your protein, either try to reformulate it to make it more stable, more soluble, try different protein constructs, look to see computationally if the protein is predicted to have intrinsically disordered regions. There are things you can do to the protein to make it more amenable to crystallization, and those should be pursued before setting up more crystallization trials to try to identify those initial crystallization conditions. Okay. So now I'm going to talk about optimization of these initial crystallization conditions. So you found one or more chemical cocktails that give crystals of your protein. So now it's time to do something to try to produce, in the case of XFEL's work, a large number of very small crystals, submicron crystals. So just to sort of reemphasize this, producing large crystals is no different than producing small crystals from the perspectives of thermodynamics and kinetics. Okay? So this is a very old quote from 1951, but it's one that I really like, and it basically says that to produce large crystals, we need to pay careful attention to pH, salt concentration, protein concentration, and temperature. The same variables hold true for producing nanocrystals. So all of the literature that talks about producing large single crystals can be applied to nanocrystals if you just think about it in sort of a slightly different way. Now, phase diagrams are just, and by phase I mean solid phase, liquid phase, gas phase. For these particular experiments, we're talking about just a solid phase of protein, so a precipitate, a liquid phase of the protein, which can be a concentrated liquid-liquid phase separation, or just the protein solution, and a precipitated phase, which can again be the protein just sort of randomly aggregated and coming out of solution or crystals. So the phase diagram really is a guide to optimization. It lets you sort of see the entire forest, the entire landscape, not just individual outcomes. It lets you put things together in a way that makes sense. Okay. So to get a true phase diagram of a protein, you have to measure the solubility of the protein under different chemical conditions. And this has been done for very few proteins. There was some early work that was done back in the 1920s, but and there's been some work in the 80s and 90s in particular that looked at lysozyme crystals. But this solubility data is basically, it's a particular crystal form, and it's at its saturation point. Okay? So if you look at this solubility data for lysozyme, you can see that it's much more soluble at a low concentration, 2% sodium chloride, and higher temperatures, 30 degrees. So you're up to 90 mg per mil. As you decrease the temperature, okay, you're decreasing the solubility of the protein. Okay, so this is one slice sort of saturation data for one protein. Okay, and you can continue with different slices for different salt concentrations, or you can look at the data in another direction here, where you're looking at a single temperature, but different concentrations of salt, where again, you can see the lower concentration of salt, the protein's more soluble, higher concentration of salt, the protein is less soluble. But the message here is that each one of these slices, these rows, is showing saturation data. Okay? Now, how does that saturation data relate to this phase diagram that I'm showing you now? Okay? The saturation data that you can actually measure in a laboratory, but which few people measure because it's a very complicated and time-consuming process to do, is just this dark line on this graph. Okay? So on the y-axis here, we've got the concentration of the macromolecule of the protein in mg per mil. On the x-axis, we have the concentration of some precipitating agent. In this case, we'll consider it maybe a salt, like ammonium sulfate. So in this very basic phase diagram, you've got undersaturated regions in white. You've got a saturated region, which is just an equilibrium state of the protein crystals. And then you get into the supersaturated regions, which are shaded in gray here. The lowest level of supersaturation is the metastable phase. And this is where crystal growth can occur, but it's not sufficiently supersaturated for a nucleation event to occur. Okay? So if you leave a solution that's metastable sitting in a countertop for a very long time, crystals are never going to form. It's going to stay a clear solution. Thermodynamically, it's supersaturated, but it's kinetically never going to be able to produce a crystal. Okay? Not in the time period that you need to produce a crystal in. Okay? As you get slightly more supersaturated, you reach into this nucleation, this labile region in that darker gray. So this is a higher level of supersaturation, and it's a level of supersaturation that's required for ordered aggregation of the protein molecules to happen. And then we go to even higher levels of supersaturation in dark gray. And at these very high levels of supersaturation, the protein molecules are many times supersaturated with respect to what you need for crystallization, and the molecules will actually randomly aggregate. So this is not a place that you want to be for crystallization. Sorry, I jumped the gun here. So again, precipitation region up here, disordered aggregation, which you don't want. Nucleation in the Soluble region, which is where you want to sort of target for your crystallization experiments, where you have ordered aggregation. And then the growth region, which is less supersaturated, where you're going to have clear drops unless some kind of a crystal nuclei is added to the solution. Now, when you're reviewing your crystallization experiments, you're going to see clear drops, and those clear drops can either be metastable, or they could be saturated, or they could be undersaturated. There's no way to tell by just looking at the experiment using a microscope. It's a clear drop. And so, in simplest terms, the phase diagram is just a sort of a collective view of the experiment's outcomes and how they relate to the solubility of the protein. Okay. Now I'm going to step back a little and use a sort of a simple concept to help relay the chemical design of the experiments here. But basically, if you think about the chemical experiments, the crystallization cocktails like a deck of cards. Okay, you could look at these cards one at a time, right? You could have the jack, the two, your ace. Okay? You could randomly throw the cards down and not really know how the cards relate to one another. Or you can arrange the cards according to the order that cards have. Like there's the suit of the card, and there's the value of the card. And we can put that on a simple coordinate system, right? And we can identify exactly where the two of hearts is going to be on that coordinate system, right? So we can do the same thing with our crystallization chemicals, basically. We can represent the entire deck of cards using a grid system like this. This would be considered a grid screen for crystallization. And all it is a very sort of refined sampling of chemical space. So in this case, we're looking at a grid screen that goes from 10% to 32%, PEG 4000, and we've got a range of pH values very finely sampled along the y-axis here. Okay. And we can populate that entire grid of experiments, and we can set up those experiments, and then we can see the outcomes, which is what you're seeing here. Okay. And when you look at these experiments, if you were to look at them one at a time, and you didn't know how they related in particular to each other, you get some information. You can tell if you had crystals, if you had precipitate, if you had clear drops, but you don't get the complete picture. To get the complete picture, you really want to look collectively at the experiments. And I just want to show you here quickly the difference that very small changes in pH can have on the outcome of the experiment. So here we're holding the concentration of PEG constant at 18%, and we're just going to go from a pH of 4.5, and you can see that we have a precipitate here. We slowly increase the pH now to pH 4.6, 4.75. You can distinctly see crystals, large crystals at pH 4.9, and smaller crystals at pH 5. Again, just very slight changes in the pH are causing a dramatic shift in the outcome of the experiments. And the same thing's going to happen if you look at the concentration of PEG as you increase it. So again, these are very small increases, very incremental increases in the concentration of the PEG. When you're doing your initial crystallization screening, it's not uncommon to have a 20% change in the PEG concentration over a series of different salts or other chemicals, buffers. So these are very fine changes in PEG concentration. And even with these fine changes, you can see that you get some very significant differences in the outcome of the screening of this grid screen. So small chemical changes can have a huge impact on the level of supersaturation of the protein. Okay. Now, when you look at all of these experiments collectively, you can start to see patterns, especially when you're arranging things on this grid, this chemical grid. So you can see that there are more clear drops. Clear drops are showing up at higher pH values in this case and low concentrations of PEG. Precipitated drops, so more supersaturated solutions, are showing up at lower pH values and higher concentrations of PEG. And crystals are always going to show up between precipitated drops where you're too supersaturated for ordered aggregation, and clear drops. Okay, so when you look at this, this is really a sort of a simple phase diagram. It's coarsely sampled, relatively coarsely sampled, but you can think of the whole thing now in terms of solubility. So you have lower solubility of the protein up here where the precipitated drops are forming. Right, the protein's coming out of solution so that it can reach a state of equilibrium. So you have a lower concentration of protein in these solutions that surround this precipitate. You have higher solubility down here where you've got the clear drops because all of the protein is in solution. It's perfectly soluble. And then you've got these crystals that are forming sort of between the two boundary zones. Now, when you look at this, you might be able to see from this diagram, but the larger crystals are forming at higher solubilities, right? So lower levels of supersaturation. So in order to produce smaller crystals, you want to drive things to higher levels of supersaturation. So if you do your initial crystallization screening experiment and you're producing crystals that appear as nice single crystals, but they're not what you want for your X-Files experiment, you want small crystals, you have to simply drive things by decreasing the protein solubility. In this case, by going to lower pH values and higher concentrations of PEG to produce smaller crystals. So in most cases, we don't have that nice grid screen when we're doing crystallization, especially screening experiments where we're just trying to identify initial conditions. Okay? What we typically have is an incompletely sampled deck of cards, right? So chemically, we're not hitting every possible card. We're just going to hit a few of the conditions. Right? So let's use this card analogy now and look at some actual data from a crystallization screening experiment that was done. Okay. In this case, we've got different buffer types going along this axis up here. These are the pHs of the different buffer types. This is PEG 400 being used as a precipitating agent at 20, 40, and 80% volume concentration. Okay. And we've got lithium bromide. In this case, it's at a 10th molar concentration, which is a constant throughout all of these experiments. Okay? So we can prepare crystallization cocktails for the screening experiment at these different points, these blue dots in this sort of grid sampling here. Okay? There's a lot of white space, which are places that we haven't produced a chemical cocktail. Again, most crystallization screens are very coarsely sampled, so we aren't going to have complete like a grid of data to show you to look at outcomes. We're going to have to sort of fill in the blanks based on what we see from the results of the experiments that are set up. So we can populate those cocktails now with the actual outcome of what happened when you take the protein and you combine it with that particular cocktail under those chemical conditions. Okay? And these are the actual outcomes from these experiments. Okay? I'll just blow that up a little. So you can see you have precipitation here, you have crystals, and then you have clear drops over here. just taking snapshots of different locations in the phase diagram, and you're hoping, in the case of producing these nanocrystals, that you're closer to the precipitation region than you are to the metastable region, but you're still falling within this Soluble zone. Okay? And this is just an example that has 16 different volume ratios of a protein for a cocktail. And just to show you the impact this can have, you can go from these highly precipitated drops to crystals to, again, precipitated drops on the other end. So you can have a really dramatic effect on the outcome of the experiment just by simply changing these volume ratios. So another way to look at this is just that you can change the starting concentration of the protein and set up these drop volume ratio experiments to drive things to a higher level of supersaturation. And so if we do an experiment where we have the 16 different drop volume ratios and we start off at, say, a 10 mg per mol protein solution, and we do these volume ratios of protein to cocktail, at the midpoint we're going to have basically a 5 mg per mol protein solution, and basically you can see you're going from this sort of larger single crystals in this case down to what actually looks like a larger crystal here, sorry, here. And looking at this, it's really difficult to tell whether you have nanocrystals or what's going on, but if you look at the SHG signal, the second harmonic that we talked about earlier, you can see that these are actually microcrystalline, nanocrystalline outcomes that we're observing, and we're changing the actual outcome just by changing the volume ratio of protein to cocktail in the experiment. Now, I was saying that if we took the protein concentration and changed it, okay, so these are the same chemical cocktails, the same volume ratios, but now we're starting at, say, 5 mg per mol protein instead of 10 mg per mol protein. You're changing the points that you're sampling in the phase diagram, and you don't need second harmonic generation to tell you that you're producing crystals and that the crystal outcomes are changing with the drop volume ratio in this case. So this is the exact same experiment as the previous one, except this one is set up at half the initial protein concentration, and you're producing these larger. Okay? So again, we're just sampling a different phase diagram. Okay? Temperature effects can be very effective, especially with batch experiments, to alter the outcome of the experiment. And I'm just going to mention it briefly because if you're not careful and you don't control the temperature, you're going to have sometimes wildly varying outcomes. Protein solubility is related to temperature, but it's also dependent upon the particular chemical cocktail that the protein is in. Okay? So you can go from protein that's more soluble at lower temperatures, less soluble at higher temperatures, as seen here, to the reverse, we have retrosolubility, where the protein is less soluble at low temperature, more soluble at high temperature. The problem with using temperature, even though it can be a great way to produce small crystals, is that practically to do an X-Files experiment, you're not going to be able to control the temperature in that room. So you're probably going to be shifting and changing the crystal size when you take it out of a, say, 4-degree environment or a 37-degree environment and try to hope to exploit during actual crystallization experiments when you can't cryopreserve the crystal. Vapor diffusion crystallization is probably the most popular way to grow large crystals. For a vapor diffusion experiment, you're taking your protein and your cocktail, you're combining them, you're putting it in a sealed container, and you're basically using a reservoir solution that has a lower vapor pressure of water to pull water molecules away from the experiment drop. So the protein experiment drop is going to decrease in volume as water is pulled away from it. As it decreases in volume, you're going to increase the relative concentration of any chemical that's present in that drop that's not volatile. So the protein concentration is steadily increase, the concentration of polymers, salts, it's going to increase, and it's going to drive the system to a state of supersaturation. Okay? The reservoir is also going to set the endpoint of the dehydration process. So again, with a vapor diffusion experiment, you're starting off undersaturated, you're combining the protein in the cocktail, and then you're dehydrating the experiment, hopefully to drive it into the Soluble zone, where you can have a nucleation event, and then eventually equilibration at the saturation point takes place. Liquid diffusion crystallization, I just want to talk about briefly. Dialysis in particular, I'm going to talk about. So dialysis membranes, or dialysis, can be used to do something called desalting. So basically pulling salt that's required to keep a protein soluble away from the protein, decreasing the ionic strength of the solution. And this is actually a great way to produce very small crystals. I'm not sure how widely utilized it is for X-Files right now. So set up a dialysis experiment. You basically have, in this case, sort of green colored line represents a membrane that has a particular molecular weight cutoff. So it won't let large protein molecules pass through it, but smaller molecules can freely pass through the membrane. So the protein's represented by these sort of red dots here. And you have a solution out here that doesn't have any salt in it, a solution with salt to keep the protein in solution here. If you basically leave the experiment to equilibrate, what will happen is the small molecules that can pass through the membrane will equilibrate against the reservoir and reach a constant concentration. The concentration of the protein is going to remain the same unless it comes out of solution, because it can't pass through this membrane. So you can use these dialysis techniques to pull salts away from your protein, or you can use them, in this case, to add salt to your protein to let it slowly dialyze in.
Did you give that headset to Joe?
Now, dialysis experiment, because
No,
the
we're
protein
not.
volume is held constant by that membrane, and it's in a little container here under this membrane, it has a very different approach through the phase diagram. So the protein concentration doesn't change. It's just the concentration of the crystallizing agent, the salt, change. Okay, so you can drive things as it equilibrates and the salt enters into the little divot that has the protein. You can increase the level of supersaturation of the protein, drive it to the Soluble region, and then have a nucleation event and have a crystal form. Okay. Now, the rate of equilibration of vapor diffusion or dialysis experiments is going to have a big impact on the size of the crystals. And there are a lot of different ways to control and change how quickly an experiment drop equilibrates, either with a reservoir solution in a vapor diffusion experiment or a liquid reservoir for a dialysis experiment. And there's a reference for a couple of papers on how to do that. But just to skip these slides, just to show you the outcomes of that. If you sort of very rapidly equilibrate a vapor diffusion experiment, you can get some very small crystals. If you do it at a slower rate, you can get some very large crystals. And the same is true with dialysis. Here we have very small submicron crystals and very large, almost millimeter-sized crystal on the right, just by slowing things down. Okay. I want to talk about pH, which is a very important crystallization variable that's easily controlled. So this is just a distribution of the pHs that have been used to crystallize proteins that are in the biomolecular crystallization database. And just to sort of give you a concrete idea of how pH can affect protein solubility, if the pH is less of the solution is less than the pi of the protein, you're going to have a positive net charge on the surface of the protein. If the pH of the solution is higher than the pi of the protein, you're going to have a negative net charge on the surface of the solution. Okay? So if you have protein molecules that are negatively charged, they're going to tend to repel each other in solution. So the protein is going to be more soluble in those solutions. Okay? If you have a pH that's roughly equal to the pi, the isoelectric point, where the net charge distribution, net charge of the protein is zero, if you take all the positive and negative charges on the surface of the protein, they neutralize, then you have a chance to actually have attractive interactions, and the positive and positive and negative charges can be attracted to one another, and you tend to have lower solubility of the protein. Okay? So to demonstrate that practically, I'm going to use the Hampton Research slice pH screen, which has a very fine sampling of pH, a tenth of pH unit increments, and it has 20 chemically distinct buffer types. And there's an overlap between the two. So these are the outcomes of an experiment where the protein was set up against this very fine gradation of pH. And what we can do is review those experiments and classify them as crystals, precipitate, or clear drops. Okay? And then we can go back to using this grid idea where we color code things to show clear drops as blue, precipitated drops as green, and crystalline drops as red. Okay? So again, along the y-axis here, we have a range of pHs from 3.5 to 9.6 and a tenth of pH unit increments. On the x-axis at the top, we've got these 20 different buffer types. Okay? And again, we're color coding the outcomes. Now in this case, the outcomes that were set up between pH 3.5 and pH 5.4, regardless of the chemical type of the buffer, produce these amorphous precipitates. They could be actually denatured protein. Okay? It looks like the protein did not do so well when it was subjected to these lower pH values. If we look at a range of higher pH values, 7.3 to 9.6, we see clear drops. Okay? So the protein is more soluble at basic pH, independent again of the buffer chemistry. But now when we zoom in and we look at a pH range of 5.4 to 7.2, what we're seeing are actually, and unfortunately this isn't distinguished, but a combination of large single crystals and nanocrystals that appeared. Okay? And these are dependent on both the pH of the solution and the chemistry of the buffer type. So if we look at this particular outcome, this is pH 6.9. This is with this tris buffer at pH 6.9. You're getting these nanocrystals, and pH 6.9, the only thing that changes is now we're using this sodium Heaps buffer, and we're getting larger single crystals forming. Okay. Now, the same thing is true with just having very small incremental changes in the pH of the solution and keeping the buffer chemistry constant, where we go from crystals that you can actually visually detect to nanocrystals, then to basically clear drops eventually. So just again, the effect of just the pH, independent of, in this case, keeping the chemistry of the buffer constant. Okay? And just to sort of drive that point home and prove that these really were nanocrystals, these are some second harmonic generation images that actually verify that those outcomes that look like they could be precipitate are actually nanocrystals. And finally, I'm just going to talk a little bit about the sledgehammer approach. So if you want to throw caution to the wind and you don't care about trying to sort of carefully use the phase diagram to produce these single crystals that are small nanocrystals that could be used for X-Fel's work, people have actually just taken large crystals that they've grown and smashed them up using something like a seed bead or a bead bug to actually homogenize the larger crystals and produce a lot of very small crystals. And these do seem to work for the X-Fel's experiments. But again, I sort of hope in my heart that we try to actually produce these nanocrystals from the onset instead of smashing up larger crystals. Just two quick final slides that I want to kind of drive home. Whether you're trying to produce large crystals or nanocrystals, the same exact principles, technologies apply. Variables are the same. You want to pay attention to pH, salt concentration, protein concentration, and temperature. And finally, think about your crystallization experiments in terms of a phase diagram. So think about that deck of cards, how you lay out the chemistry, and where your outcomes would fall in that chemistry, which tells you the level of supersaturation that the experiment is at and can help guide you toward producing these nanocrystals instead of large single crystals. So that's it. If anyone has any questions, I'm happy to try to answer them. Thanks for your attention.
Okay, thank you very much, Joe. Does anybody have any questions? Anything at all? So I have a question. So earlier on in the presentation, you said that you won't get a UV signal for amorphous precipitation, but you will get a UV signal for microcrystalline precipitation. So do you have any idea why that is?
Let's see. You're cutting out, but I think your question was, why do you get UV signal from microcrystalline precipitate and not from amorphous precipitate?
Yeah.
And the microcrystalline precipitate is more concentrated. The protein is more concentrated, so it's actually able to give off a signal. Whereas the amorphous precipitate, the actual concentration of the protein is lower. It's more distributed, so you can't detect it over the background signal that you might get from just the solution itself.
Okay, thanks. Okay.
So I have a question. When crystallizing the protein using salt reagents, how do you know that the crystal is that of just the protein?
Very good question. So I didn't put these slides into the deck, but there are a lot of different ways that you can sort of verify that you have a protein crystal instead of a salt crystal. One of them is to add something like methylene blue dye to the drop. The smaller crystals will actually take up the dye. You can take a probe, like a steel probe, and actually look under the microscope and try to crush the crystals, and you'll actually be able to hear a crunching sound with a salt crystal. And salt crystals will tend to sort of shear, whereas a protein crystal will just crush or crumble like a piece of cake, and you won't hear anything. You can try to harvest the crystals, wash them, and then run them on an SGS page gel to see if you actually get a band that migrates to the molecular weight of the protein. UV fluorescence is another way to tell. So salt crystals typically won't have a UV fluorescence signal, whereas the protein crystals, if the protein contains tryptophan, will give off a UV fluorescence signal most of the time. So there are a number of different ways that you can sort of distinguish between the two outcomes.
Ask that question to him then? Is that what he's talking about?
To Joe.
So we have a question in the chat window here, and that is, if a crystal is not birefringent, will it also not show up in the sonic?
That's a very good question, and actually I don't have a definitive answer to that, but I believe that is true. So the sonic requires chiral crystals, and it requires the crystals, there are instances where crystals that you would think would show up under SHG don't show up. And yeah, it depends again on the crystal symmetry and orientation, so I'm not absolutely certain, but I think the two techniques should be comparable, although the sonic is more sensitive, so it's able to detect much sort of weaker signals than you would be able to detect using a standard sort of cross polarizer on a microscope. And it's also, the sonic's a confocal technique, so it actually takes slices through the drop to have reduced background noise. So the sonic is more sensitive, and I believe it could detect things that you won't be able to detect using a standard microscope just because of the increased sensitivity. But I'm not certain if the physics behind it, how they relate to the cross polarization of birefringence.
Okay, thanks. So do we have any more questions? So thank you, Joe, and thank you everybody else for tuning in.
Thanks.